you can ask them doing the hardware.
All right, yeah, so until now we've seen VAS, integer VAS, and pushdown integer VAS. And I'd now like to talk about a broader picture result that tells you, for a broad class of infinite state systems, what is the complexity of bidirected retrieval. So we had our example in the beginning of some, not bidirected, but some infinite state system. And we saw that we can interpret the same drawing as a pushdown, as a VAS, and also as a ZVAS. And this is the basic observation that leads to this notion of valence systems that generalizes many types of infinite state systems. So the idea is to take a set of instructions that can come in as positive and negative instructions, and to look at which instruction sequences are valid. So in the case of a VAS, or in all these cases, we always want the set of instruction sequences that leave the empty configuration to the empty configuration. So consider a word over A and B, and A bar and B bar. And they can be, so let's first consider them as pushdown instructions. Now, when is a sequence over A's, B's, A bars, and B bars, when is that a valid sequence? We want it to be valid if it brings the empty stack to the empty stack. And the set of valid instruction sequences is the JIT language, right? And you can describe that as follows. It's exactly those words that you can bring to the empty word by deleting A bar and deleting B bar. Right? If you have a sequence of push and pop operations that go from empty stack to empty stack, then of course you can always do these reductions and arrive at the empty word, because it's well nested. And the converse is true as well. If you have a word that you can reduce this way, then it will be a valid pushdown run, and you can show that by making the opposite observation. If you can build up the word by inserting A bar and B bar, then it's a valid pushdown sequence. So that means you can characterize a pushdown by these two rewriting rules. We can characterize actually the class of all pushdowns by these two rewriting rules. It turns out we can do the same for the other types of systems as well. So for n counters, you can do these reductions. And you can also commute instructions for distinct counters. You can take a moment or let's take a moment to understand why this exactly characterizes the two VAS. So two because we have A's and we have B's. On the one hand, every instruction sequence of A that brings the empty configuration to the empty configuration of 2 VAS can be reduced in this way. Well, because you can sort them by counter. First, you do all the instructions on the first. If you have a sequence of instructions, these commutation relations just allow you to sort by counter. First, you do everything on the first counter, then everything on the second counter, and then you can understand them as a pushdown. Then, of course, you can reduce them to the empty ones. And conversely, whenever you have something that's reducible to these by these rules to the empty word, you can interpret it as a 2 VAS just by building up the word and always interpreting if it's an A and B, then you interpret it as the first counter, and otherwise it's the second counter. Right? This is easy to see. You can even do this for Z counters, but then you need a third. You need to add yet another rule, which is that you can now also flip A bar A and A bar. Right? Because now it doesn't make a difference if you first subtract and then add. Right? So if you just have one Z counter, then then you have a valid instruction sequence if and only if you have just the same number of A's as A bars. Yeah?
Would it make sense to actually just in the push down add this instruction and in this
Yes.
way sort of have a free group?
Exactly. Yes. Exactly. We will do a lot of that.
Okay.
And now the idea for this general class of systems is to systematize this. So actually, you can now note down for each kind of letter pair what you can do. Can you invert it with its own inverse, or can you commute it with the other instructions? This gives you a graph. So in this case, you can only invert with the own inverse in the right order. Then we draw And so let's say the left one corresponds to A, the right one corresponds to B, then we draw no edges. And here we're allowed to commute elements, so instructions from different counters, so we draw an edge between the counters. And here finally, we can even commute each instruction with its own inverse, and then we also add self loops. And now the idea is to go in the opposite direction and look at this for every graph. So for every graph, you can now define rewriting, exactly these rewriting rules. So for every node, you have the rewriting rule A and A bar goes to the empty word, and an edge between two allows you to commute different instructions, and the self loop allows you to commute even with its own inverse. So this is just the definition that I just said, just repeated. And we say an instruction sequence is valid if it reduces to epsilon using these reduction rules. So let's see some examples. So as we discussed, this would give you 3 Z counters, right? Because you can commute the different instructions, and each instruction commutes with its own inverse, so you get 3 Z counters. And here you have no commutation rules, only the reduction rules, first positive and then negative. So this would give you a push down on 3 stack vectors. And this we basically also discussed, it's just the case of 3 instead of 2. This would give you 3 encounters over 3 lists. Now this is not so easy to see immediately. But you can, if you group the vertices, the 2 left ones, if you just had the 2 left ones, it would be a pushdown. If you just had the 2 right ones, it would also be a pushdown. But now you have edges everywhere in between. So it means you have 2 commuting pushdowns. That's the same thing as just having 2 pushdowns. Right? As we saw, commuting always means you have 2 independent mechanisms. If you draw it a little nicer, if you flip the, what do you have to flip? Right, if you flip the topmost 2, left and right, then you get a square. And 2 pushdowns is the same thing as a termination. All right. And a final example that you can understand using a similar argument. Does anyone see what this would be? Yes, exactly. So the topmost, so Sylvain got it right. So the 2 topmost, they give you a pushdown, and then you have 2 extra counters. So this would be a pushdown to 2 best counters. So there's been some work on understanding the connection between picking a graph and computational properties of the resulting model. And one of the results is describing, at least partially, when reachability is decided. So as we saw, pushdown maps are a special case, and as probably everyone who knows whether reachability is decided or open, but there's a result that at least says if we exclude all pushdown masses, then we know when we have decidable reachability. And it's the following. So the models that come out as decidable can be constructed as follows. So the simplest case is you just have a VAS. So this, for me, represents a 3 VAS. So brown counters are always ones where you have to stay in one square. And what you can do is you can build stacks where every entry is a set of VAS counters. Okay? So that means on the topmost entry, you can work as on a VAS, and whenever it's empty, you can do a pop operation, and then you work on the one below. You also have a push operation, and if you do that, then they all stay as they are. If you start a new entry, and then you work on that. Okay. What you can do in addition is add Z counters. So Z counters are ones that can go from 0. I draw them in blue. And then you can play this game again and look at stacks that contain these guys as stack entries. Right? And then you can add Z counters again, and then you can alternate as many times as you want. So these are the models for which we know decidability. So in other words, you can start with N counters, you can build stacks, add Z counters, and alternate between the two. So this class is called SC plus minus because in the beginning you start with positive counters, but after the first time you can only add Z counters. That's where the minus comes from. So it's known that reachability is decidable for these. And for every other graph, either we know it's undecidable, or it contains pushdown mass. So we don't know whether reachability is decidable. So this is the state-of-the-art decidability. And what I wanted to talk about is the bidirected reachability for these models. So this slide is just about ordinary reachability, so not bidirected, but ordinary reachability. So because the question was, is it even true in this class that reachability is always easier in these systems, or bidirected systems? And the result is the following. So the first result, if you take a particular graph from this class, so all these types of storage, so counters, stacks, and so on, they correspond to graphs, as I described. If you take one of these graphs from this class, then bidirected reachability is either complete for deterministic log space, and that's the case if and only if the graph is a clique, or it's complete for column number time. But you have to keep in mind that for every graph, all the number of counters are fixed. That's why the complexities are so low. But here we have a complete description. So it's always either deterministic log space or column number time. I forgot to mention, this is in LIX 22, the first paper we had on this, together with Moses Ganazi and Rupak Majumdar. So if you reinterpret this graph description in terms of storage mechanisms, if you only have counters, so a bunch of N counters and a bunch of Z counters, then you're L complete. But if you have some stack, then you're P complete. All right. And now you will also wonder, what is the complexity if the graph is also part of the input, right? This would be the setting of all bidirected VAS, right? Because then the number of counters is part of the input, so that means even the graph is part of the input. And this is what I'll talk about now. Then we get away from these super classical log space and polynomial time classes, because we get problems where the that seem to lie in between. Complexities that seem to lie in between. So now we're again at this linear Diophantine equations. So as I mentioned, this is in polynomial time. But it's not known whether this is p hard. This is still open. And that's why we just said we look at the class ILD, which is all the problems L reducible to ILD. And many of our problems will be ILD complete. Right, so this ILD is between log space and polynomial time. So now we want to understand what's the complexity of the graph as part of the input. So in technical terms, that means we look at a class of graphs, and we want to know if our input is restricted to that class of graphs, what is the complexity? So for example, bidirected VAS reachability would be the class of cliques without self-loops. Okay, so let's look at any such class of graphs, but they all should be in this class where we know that general reachability is decided. That's what our pentacotomy is about. So we call this class n-bounded if the number of n counters in this class is bounded. So all the cliques in this class of graphs, they have a bounded number of n counters. So at most 3 VAS or something, right? That's what we meant about it. So you can already know from what I said before. If we're not n-bounded, then the problem is x-VAS hard, right? Because if we're not n-bounded, then we're n-unbounded, and then we can reduce bidirected VAS reachability to it. Z-bounded means the number of Z counters that can occur, meaning the number of nodes with a self-loop. And then there's also alternation bounded. I mentioned to you that all the mechanisms in SC+, they are obtained by alternating, building stacks and adding counters. So outbounded means we do only that bounded number of times. Okay. Does that make sense so far? Okay, this allows us to state the result. And also, right, we also say we're closed under reduced progress. Otherwise, we get some pathological things where the problem is only easy because all the graphs are like Ackermann size or something. This is just a, you can forget about this assumption. This just rules out pathological exceptions. So the class of graphs that we want to allow as input should be closed under reduced progress. Then bidirected reachability is L complete if the graph has no stack, so meaning there are no two edges without an edge in between them. And it is n-bounded and z-bounded. So in other words, there's only a fixed number of VAS counters and a fixed number of integer counters. Then it's incomplete. And this, for example, uses Reingold's result. And the reason is, if you have a fixed dimension VAS, then the bounds from the Meyer paper tell you if you're reachable, then you're reachable with at most doubly exponential values. If you fix the number of counters, this will be a fixed bound. And that means you can turn every input VAS into an undirected finite graph, and then reachability is a deterministic consequence. It's ILD complete if you have a fixed number of n counters and an arbitrary number of z counters. So it's a clique, but you have a bounded number of VAS counters and arbitrarily many z counters. And the reason is the algorithm essentially eliminates the n counters. This uses some stronger results by Kopenhagen on this connection between VAS and polynomial ideals to eliminate all the VAS counters by bounded counter values. And then for the remaining z counters, you apply solving linear divergent equations. It's P complete if the graph contains a stack and you're n-bounded, so you have a bounded number of VAS counters, and alternation bounded. And this is the case where we're not quite at a pentacotum yet. So here we only have an upper bound. If we know we have a bounded number of VAS counters, but arbitrarily many alternations, then we only know we're in exponential time. The reason is that it's exponential time is if you do this, a construction similar to what I described for integer pushdown VAS, you get equation systems that are compressed. And this compression is so that if you have a bounded number of alternations, it's still polynomial, but with a high, but like with a fixed exponent. But if the alternation is part of the input, then the compression compresses exponentially large equation systems, and that's not clear if you can do it or not. And finally, in all other cases, you're X-space complete. Because in all other cases, you're not n-bounded anymore, and then you get X-space hardness from this. So this is almost a complete picture. So for example, these are, I think, we mentioned already some of them. So for ZVAS, you go from NP down to ILD. For pushdown VAS, you go from NP complete to P complete. And even if you have a fixed number of alternations of building stacks and other counters. And I could also mention there is a class of groups, a subclass of right-angled Artin groups, for which this result yields polynomial time subgroup membership. So this is a way where bidirected results from infinite state systems can give back to the group theory. Right. Any questions about this?
What about mutual reachability, which is like in between?
I don't know. Good question. Yeah, I haven't looked at this. I now know that for pushdown VAS, that covers, then it's the same as stable reachability, as I learned during my quiz. But yeah, here this is a nice one. All right. So this was now all on results on systems where we know that ordinary reachability is known to be decidable. And all of these results were bidirected, then suddenly it becomes easy. Now the last section will be about pushdown VAS where ordinary reachability is not known to be decidable. And then we go from not known at least to decidable. Right, so pushdown VAS is syntactically the same as a pushdown integer VAS, except that the configurations now have to have natural numbers in the configuration. So, I was told this is the FANCAT problem, whether reachability is decidable there and it's open. And in the bidirected case, one can show it's decidable in Ackermannian time and tau hard. And I will not talk about the complexity results of this particular fact, but about decidability. And I think I can do the improvement for it. Because it's very simple, surprisingly. Right, so decidability in dimension 1 was known before by Kjellström and Pavlogiannis, and they reduced to the decidability of coverability in one-dimensional PLS. Right, but its decidability holds even in arbitrary dimension. All right, and the proof uses a very nice concept called slices, which for some reason have been ignored in the literature for many years. I'm not sure why. So what is a slice? A slice is a set of vectors with a particular closure property. So whenever you have a vector u in your set, and you have a vector u plus v in the set, so these differences are always natural numbers. So the u plus v, that's another way of saying it's larger than u. And u plus w is also in the set, then you can also add both of these differences. So it's a little bit like a local monoid condition, right? Whenever you're above some element, you're allowed to add all the differences above it.
It looks a bit like amalgamation.
Exactly, yes, exactly. It's exactly amalgamation, except that you don't have to pay attention to WPO underneath. I find this very curious, yes. Right, so whenever you have u, you have something larger here, something larger here, you can close the diamond. That's what it means to be sliced. So for example, upward closed sets. Right? If you have an upward closed set with respect to conformwise ordering, then you slice. Another example is solution sets to linear equation systems. If you have two solutions, three solutions, right? These three guys here. This is only possible if V is mapped to 0 by A. That means you might as well have both. And congruence relations. That's a simple observation. And the really nice fact about them is that they're always semi-linear. So you know nothing about the structure, you only know they have this closure property, similar to upward closed sets. Just by knowing this closure property, you know it's semi-linear. And this can be used in this proof. Right. Not sure if I have to define semi-linear. It's first definable in natural numbers with addition. And this is also called Pressburg arithmetic, which is a decidable logic. That's all you need to know. Not semi-linear. Right. This proof necessarily is not constructive because there's no representation with respect to which it could be constructive. So you only know it's closed, and then you already know there exists some semi-linear representation. All right. So let's prove this. Any questions so far? Yeah?
Yes, I have a question. Do we have some geometrical characterization of the seminar sets that are slices?
No. I think very, very little is known about slices. We have found an obscure master's thesis from MIT in the 80s where we couldn't even get the PDF, only the abstract. And it makes a nice observation, which is that every semi-linear set is a homomorphic image of a slice. And then we managed to prove it after reading this. We couldn't get the PDF. It's not hard. But yeah, they have been criminally neglected in my opinion. I think they're super nice. Because congruence relations, I mean, upward closed sets, this has been exploited very well, that they're semilinear. Semilinearity of congruences has been exploited very well. But slices, I think, seem much more powerful because you have a much better chance of finding them in the wild, right? To show that something is a congruence, it's a very algebraic notion. But slices, that seems to be something that you find much easier because they generalize both upper closed sets and congruences. Right.
Is it hard to show that every slice is semilinear?
I'll do that right now. You're asking amazing questions.
You can pay us later.
All right. So first of all, you can consider for every element in your slice this set S minus U, which means all the elements, all the differences that you can add above the U to still stay in S. So it's the set of all V, so that U plus V is S. And the slice condition just says that this is closed under addition. So this is the monoid. This is S minus U. Right? But we're not looking very much at this monoid, but we look at the monoid generated by its minimal elements. So we take the set S minus U, we take out 0, because otherwise it would be one element. And then take all the minimal elements of this monoid, and take the monoid generated by, take the monoid generated by all these minimal elements. The nice thing about looking at this MU instead of S minus U is that this is obviously semilinear. Because there are finitely many minimal elements, so this is already semilinear. So in other words, we take all the sums of minimal elements of the set. Okay, this is the key notion. Easy observation, the entire slice is the union of all these patches, where you take U plus this monoid. And trivially, because this monoid contains the 0 element, so U plus MU contains U in particular. This is trivial. And also, each of these patches is semilinear, because MU is semilinear. And the whole proof is to observe that actually you only need finitely many of these patches. So actually only finitely many of them are distinct. That's the proof. Right, this is why it's semilinear. But I don't think I need to say what it means. Right, so we will show that S is actually covered by finitely many. And this, of course, implies semilinearity because a finite union of semilinear sets is semilinear. So the first observation is if you have two elements from S, and they have the same monoid, then already the patch of the larger one is already contained in the patch of the smaller one. Right? This is a natural step on the way to showing that it's only finitely many. If you have a larger one, then it already covers the smaller one. That's the moral of the letter. And this is not hard to show. It's a little subtle, but if you know this, then first of all you can observe that all the elements between U and V, if you look at their monoid, it must be the same monoid. And the reason is, if some element in between U and V had a monoid that were larger than MU, the only way this can happen is that this element in between, this W, has a minimal element that's smaller than the minimal element of U. That is, But if that were the case, V would also have one, because this element you could transport it to V by the slice product. So you know that every element in between U and V also has the same MU. And then you can show the lemma by saying, now from U to V, I can get by only walking along minimal elements. First I take a minimal element above U, that's still below V. Then I take a minimal element above that guy, that's still below V. And I do that again and again, until V is minimal with respect to the last guy. This has to happen at some point, because there's only finite space. And then the first observation shows that all of these elements on this path, they all have the same MU monoid. And also, so that means we just have to show this in the case that V is minimal above U. then it follows by conjunction. But in that case, it's trivial because then if V is minimal above U, then V is already contained in U. And then of course it's okay. So if V is above U, and they happen to have the same monoid, then the seemingly larger patch is already contained in the seemingly smaller patch. Now we can show that there are only finitely many distinct patches. If that were not true, then you would find infinitely many patches, each of which contributes something the patches before have been seen. So you can put them in a sequence, and then of course you can assume that you have an ascending chain. But if you have an ascending chain, then at least these different sets, they must grow because of this Lies property. And if they grow, then also their upward closures grow. But if their upward closures grow, then that's an ascending chain of upward closed sets, so it must become stationary. So two of them must be the same. But if these two upward closures are the same, then the two monoids must be the same. Because the monoids are generated by the minimum alpha. So if the two upward closures are the same, in particular the monoids are the same. But then, as we've seen, they have the same monoid, and uj is larger than ui, but then the patch of uj is contained in the patch of ui, but that's a contradiction, because we assume that everyone would contribute something. And that's it. Questions about this? All right. So now how do we use semilinearity of slices to show that reachability in bidirected p-wise is decidable? So first of all, we look at the empty stack to empty stack reachability relation. So for any pair of states p and q, we look at all the pairs u and u prime, so that from u you can get to p prime. And then it turns out that this is a slice. And that's very simple. Suppose you can get from u to u prime, from u plus v to u prime plus u to v prime, and the same with adding w and w prime. Then you just go back and forth. So you first replace the u and the v by u prime and v prime. That you can do because of this guy. Then you go back and replace the u prime by the u because of bidirectedness. And then all you have to do is replace the u and the w by u prime w prime, going back to q. So that means the pair of this guy and this guy is intercepted. So that means we already know the reachability relation for every pair of states is a slice. But not effectively. So this is not the proof yet. But it turns out there's an easy way of detecting if you found something good enough. It's not quite the reachability relation, but at least a certificate for non-reachability. And this will give rise to an algorithm like Jérôme Leroux's algorithm on reachability, because you will be able to certify non-reachability by some similar object. And this is closely related to a notion by Dmitry Chistikov, Rupert Majumdar, and Philip Shepard, where they were interested in certifying non-reachability in Push automata. Now the question is, can you decide reachability in subcubic time? And they showed that non-reachability can be certified with a quadratic size object. And so these two types of invariants are very closely related. So we observe that RPQ are the smallest family of sets. So this is an inductive viewpoint in this sense, where for every edge you're in the reachability relation, and even starting with any configuration. And if you compose the reachability relation from P to Q and from Q to R, you're in the relation from P to R. And finally, you can translate reachability across pushes and pops. So if you can push from P to P prime, and you can pop from Q prime to Q, then everything you can do from P prime to Q prime, you can also do between P and Q, right? Because you can first push, do your thing, go back. Right, and they're the smallest family with this property because if you have this property, of course, you catch everyone. Right, so concatenating runs is the second thing. First, you have every length 1 run. Then, if you make it longer by concatenation, you apply this. And if you make it larger by making the stack higher, you apply the thing. So now you can observe that if you have a semi-linear set with all these properties, and it doesn't contain the pair where you want to know reachability, then you can conclude there can be no reachability, because it's a saturation invariant. It's not an invariant under the reachability relation, but it's an invariant under the saturation algorithm of push-down automata. Right? These conditions come from the classical push-down saturation. So we have two semi-decision procedures. One just looks for runs, and the other enumerates semi-linear sets. And if it has one, it checks if it is a saturation invariant, and that it doesn't contain the reachability between your source and your target. Right? So when one of them terminates, of course you know you have the correct answer. If you find a path, then of course you're reachable. If you find such a saturation invariant where that does not contain 0 to 0, then of course you know you're not reachable. And the fact that the real thing, the real RPQ is semi-linear means you can also find one. That shows termination of the algorithm. Questions? Super simple. So this just gives you decidability. I also talked about Ackermann upper bound. And here I just sketch what type of methods we use. So first of all, you can reduce to the case that you just have one state by using this encoding. You encode the states in 2 extra counters. And then you observe that the reachability relation is a congruence, which, as I mentioned, is a special case of slices. And the reason we use congruences in that proof is that algorithmically they're much better understood than slices. As I said, slices have been really neglected. And congruences you can work with because you can always translate them into polynomial ideals, apply results about Gröbner bases, and then translate it back to your congruence. And that's what we did. So the algorithm does the following. It performs saturation steps. So I mentioned these translations, these closure properties of RPQ that you have to have. We apply them, we make the set larger, because we know everything you can produce will still be in the reachability relation. And then after making them larger, we compute the smallest congruence containing the set we just computed. Because we know that will also not get us out of the reachability relation. And the reason we have, and this particular step allows us, permits a complexity upper bound. Because there you can use polynomial ideas and Gröbner bases to compute the smallest containing congruence. But containing the smallest containing slice of a semi-linear set, there's no complexity upper bounds. So that's why here we use congruences, because one can use the polynomial stuff. This one can do in tower time, and as Jérôme Leroux has shown, this step could even be done in doubly exponential time. But this wouldn't improve the overall upper bound, because this tower operation is only one step in the algorithm. Termination is then guaranteed by a length function theorem. So because if you do this, you make your set larger, compute the smallest containing congruence, then make it larger again, and so on. If you look at those steps where you have a congruence, you get an ascending chain of congruences. And they satisfy, and congruences satisfy an ascending chain condition. And that's the reason the algorithm terminates. And you can then even get an Ackermann time bound by assigning to each congruence an upward closed set. There's a way of transforming the congruence into an upward closed set. And then to these upward closed sets, apply a length function theorem that tells us this sequence of upward closed sets will terminate, and therefore the sequence of congruence will terminate. But this translation to upward closed sets was I think what took us the longest. I mean, we thought the reason congruences are semi-linear is because of upward closed sets, so somehow you must find a way, but this was, I mean, I can follow the proof, but it's still weird that you can do this translation. Somehow, it remains to be understood. But yeah, this gives you the Ackermann upper bound. There's a Tower lower bound, and this uses a technique by Ranko Lasic and Patrick Totzke, who showed a Tower lower bound for general PVAS back in, when was it, I think 2014. Of course, now it's obsolete because we already know for VAS it's Ackermann hard, but the technique is good to have because it translates to a bidirected set. Questions about this?
What's your conjecture? Is Tower complete? Ackermann complete?
I don't know. Until this morning, I would have said it can't be Ackermann. But then people told me, well, but mutual reachability is already as hard as mutual reachability is already Ackermann hard because it's just as hard as general reachability. And mutual reachability, in the case of VAS, is in X space. So my intuition was that since bidirected reachability in ordinary VAS is much easier, it should also be much easier, and it should also be something elementary in, I don't know, it can't be elementary, but something primitive recursive for push-down VAS. But that argument kind of, I don't know anymore. Maybe it's Ackermann complete. Right, and the last thing I want to mention is that in the one-dimensional case, one can get a p-space upper bound. So how do we do this? So we want to know, can we go from p to q from 0 to 0? And now the 0 is a one-dimensional 0. So first of all, there's a nice observation by Kjellström and Pavlogiannis in Poppel 2022 that in the one-dimensional case, you can reduce bidirected reachability to two problems: bidirected integer PVAS and coverability in bidirected PVAS. And the reduction is as follows. So suppose you have algorithms for these two. Then first you check, can you cover Q0 from P0? The answer is no, and also the other way around. The answer is no to at least one of them. Of course, the answer for reachability is also no. But if the answer is yes to both of them, then you check if you can even cover one. Then, if the answer is no, then you must be reachable. Because that one covering path for 0 must have even been a reaching path. If the answer is yes, then it remains to check reachability in integer PVAS. And why is that? And this last part is the argument that fails in general PVAS, otherwise we would have decidability. Why does this suffice to check integer PVAS reachability? Well, because we did all these checks, we know that we can go from P, so since we know we can cover from P0, we can cover Q1, that means we can go from P to Q by increasing the counter. We also know we can go back while at least not making the counter smaller. So by putting the two together, we get a loop that increases the counter from P. We have a P loop that makes the counter larger. And the same argument gives you one for Q, a loop that makes the counter larger there. So then it's a classical trick. Make the counter larger and larger and larger and larger and larger and larger here with the same L, by taking some common multiple. And then if you know integer PVAS reachability in between, then that's reachability in general if you make the L larger. Very nice observation. Right, and so all we need to do for the p-space upper bound is to show that coverability is in p-space. An interesting point here. For this part, even though we can do it polynomial time, as I mentioned. So to get all of this down to polynomial time, which I think is the right answer, all that would be left to do is do coverability. But I don't know. I don't know. All right. So this is just so it remains to do coverability in p-space. And what we do is, again, saturation error. So we compute two quantities. We try to compute for any two states the smallest hurdle from which to execute some run. So the smallest m, so that you get from m to q to something that's at least m. In other words, the smallest drop that you can have in the path. And we also compute the smallest m that allows you to make the counter as large as you want. So the smallest m so that you have a run that strictly increases the counter value. Because if you're above that bound, then you know you can go anywhere, right? Because you can first make it as large as you want and then or as large as you need and then go where you want to go. And then the algorithm does the following. First, it finds some upper bounds for these values. And that's easy. You can just do ZP-VAS techniques, right? You know that in a PZ-VAS, if there is a run between any two states, there is one of at most exponential length. You take any word in the context-free language, it's at most exponential length. So you can compute some upper bounds. What I did not write on the slides is also for the value of this C, you also remember the difference that you can do here. You just remember. And then after saturation, you try to improve these bounds. It's clear you get p-space because all the numbers you look at all the time are at most exponential because you start from something exponential and you go down. And you try to improve in the following way. If you either you find a new edge, then that gives you a new upper bound, of course. Or you combine runs, as we've seen for the saturation invariance, right? If you find a run from P to Q and one from Q to R, then that gives you new bounds for P to R, and so on. And the same with pushes, same idea. Right? If you have bounds from P prime to Q prime, then you percolate those bounds to Q. So now you might ask, well, why can't we just do that for the simple p-space thing for general p-VAS? Because the following doesn't work in general p-VAS. The observation is that if you always improve these bounds, so improving these bounds means finding new paths. And what you exploit in the bidirected case is that there's always one path that's better than the other. Right? In a general p-VAS, it could be that you have one run that uses a smaller drop, but in return it gets you to a higher value. But here, this doesn't really happen. It can happen, but you can use it. So suppose there was one run that gets you from m to m plus delta, and another run that needs to start from some higher value, but then is also larger than, but also gets you a larger difference. Right? If you wanted to understand all possible p-VAS runs, you somehow need to use both of them because one of them might be more useful than the other in some situations. So sometimes you need one to get a better bound, and sometimes you need to use the other. But here this is not the case, because if you have this, you can again combine the two. Suppose you have these two runs, one with a lower hurdle, one with a higher effect, then you can bind the two, and then you have a loop on P with positive effect. So when you find such two paths, then you just update UP. So that means what you know in CPQ and UP is always, it always covers all the runs that exist. Right, that's it. I have some open problems, but I decided to save them for the future lectures.
what is known about two-dimensional bidirected reachability? So the lower bound needs arbitrarily many counters.
Ah, right. I think, do you remember, we had there was something like, I think 6k plus 2 was the expression. So that if you want to be k-fold exponential, you have to have 6k plus 2 counters. So that doesn't tell you anything about 2 counters. Yeah, it's a great thing to work on. I know.
Yes.
I have two questions for valence systems. So one thing is, have you thought about, so we are working about this on this one counter problem, which in a sense has like on one counter increments, decrements, and so I'm saying for other people, and push down operations, something like multiplication and division by 2. So I'm thinking, could you try to characterize such systems which somehow have push down and thus operations, but not on different counters, but together in some kind of generalized valence systems?
That's a good question. I have no idea, but it's worth trying. Yeah, that would be really nice.
And another question is, so you said that you can characterize valence systems into your system of like stacking and adding Z counters, some undecidable guys, and some guys which include push down bus.
Yes.
So would it, if we let's say know at some point that push down bus are decidable, does it mean all the other guys are decidable?
No.
No.
There will be a whole hierarchy. So if push down VAS turn out to be decidable, then it's the first level in a hierarchy, and the hierarchy is again alternating adding counters and building stacks. So if you, well, it's not the first level. The levels lower are just known to be decidable. So if you just have counters, it's a VAS. If you have a push down of VAS configurations, then this is also known to be decidable. It's a very simple argument. You just do a saturation procedure with a bunch of VAS reachability creepers. The first interesting case, the first open case, is when you have push down and counters. So the first case beyond that would be a push down of VAS configurations with additional VAS configurations, and then do the whole thing from there. Then build stacks out of those, add counters again, and so on. So I'm hopeful that the same techniques that seem to be the best candidate for PVAS would even work in the whole hierarchy, because you also have run embeddings in this entire hierarchy. So this is what we observed in the paper with Silva and Yia and Ashwani Anand, that this entire hierarchy has run embeddings with amalgamation operators. So if you manage to, so if the ideal computation approach works, it looks like also a good candidate to work for the entire hierarchy. And if that is true, that would be a characterization of everything that's decided. And there's reason to hope that all of this does work. I mean, of course there's reasons because we understand resonance on it. But the other reason is if you restrict valence systems to the case where every node has a self loop, then you get a group. Then so as Michał suggested, you get, in the case where you just have 2 vertices without edges, then you get a free group, but you get all kinds of other groups, and they're called right-angled RT groups. And for those, there is a characterization of when reachability is decidable. And if what I said with this whole push-down VAS hierarchy turns out to be true, then the characterization would be exactly the same as in the case of groups. So it would generalize this result about groups much further. And yeah, so the group result is an indication that this is probably is a completely separate reason for why this is probably true.
Is there a notion of balanced systems with data? Where,
Not yet.
when,
Not yet.
I guess my follow-up question is for the crowd: is bidirected reachability solved for an ordered data picture net?
It is.
It is.
It is.
It's not public.
It is not yet published. Accepted.
Because then maybe there would be like a more
Actually,
general.
no. Bi-reachability it's proved. It's shown last year. Mutual reachability is also solved recently and accepted as a progress.
Yeah, so indeed, it would be super nice to extend this notion of valence systems to something with data. Yeah.
Are there further questions? Yes.
Yes. So, I have a question. I'm wondering if it's possible to use the techniques you presented in order to get complexity bound for different tasks. For example, the collaborative problem is equal to 1. I know that the problem is decidable, that there is some complexity around. Do you think it's possible to improve?
We haven't tried.
Could you repeat the question?
If maybe the techniques here could be used to improve, to get complexity upper bounds, I mean to improve the not printed but kind of known complexity results for one-dimensional p-VAS coverability.
Because I remember that in order to solve that problem, you usually produce this kind of C and mini functions. But in order to compute those functions, the numbers are larger. Does it make just linear?
Definitely worth a try. I mean, I haven't tried.
Any further questions? Not, let's thank the speaker again.